Let me introduce myself. My name is, can you hear? Yeah. Can you hear now? So, yeah. So let me introduce myself. My name is Senthil Rajagopal, and I work for AMD as a functional safety and cybersecurity manager, responsible for software safety certification of AMD's programs, and as well as the Xen hypervisor. I think it's not picking up my phone. So speak loudly. Okay. It'll take from here. It take from here. Okay. So a bit introduction. So I worked on different companies, safety certifying software, and some open source software as well, and design consultation with different automotive and industrial OEMs for the functional safety compliance. So I have been working on this domain for almost more than 15 plus years. That's even before the automotive functional safety standard was initial draft was published. Uh, so I closely work with the AMD's Xen engineering team to make sure that we reach the safety certification goal. So today's my slides not going to be more technical. It's going to be a little bit of more abstract level compared to other slides you have seen so far. So talk about taking a simple use case of automotive. So it's uh, so I take a software-defined IVI or infotainment domain controller and try to explain why hypervisor is an architectural necessity when we consolidate all the workloads with mixed criticality. And then I will explain how we do the uh, then I try to explain how we do the safety certification for the Xen hypervisor. I also explain uh, the rising need of automotive cybersecurity certification need and how we are going to compliance with the automotive safety security as well. So if you understand the concept from a functional safety standpoint, I think the same logic will apply for automotive cybersecurity as well, because we are going to talk about isolation and freedom from interference. That's all same logic, which is required for both functional safety and cybersecurity. And also explain about what methodology we are following to safety certify and the current status. So there are a lot of overlap. You have been listening to all the slides, all the sessions so far. So let me start with a simple history, how we reached and where we have now. So we started with in 1930s and 50s in a simple car radio, right? I mean, it was a very simple function with AM radio receiver. Uh, it was serving only as a radio receiver. So 1930s to 50s model, you have it's all mostly based on analog and electromechanical systems. There is no microcontroller, no software. So then we moved towards personal media focused, means that customers wanted to have their own media experience in the cars. Then it started with 4-bit to 8-bit microcontroller based systems with the simple firmware where the customers can have a cassette player uh, or some media disk. So then we moved towards a little bit of more sophisticated system with integrated and connected. So you want to have Bluetooth communications and GPS navigation and Windows Media, maybe 16-bit to 32-bit microcontrollers with homegrown operating systems, or you see that time it was QNX and VxWorks. Windows Automotive was very popular during that time. So, so, so far we had all discrete systems. Each electronic control unit has their own specific functions and a lot of wirings and complexities. Uh, when we try to consolidate the systems to reduce the overall cost and also the flexibility of the systems, it became more and more software-defined systems. So then we have a concept called software-defined digital cockpit, uh, started with the new operating systems like an Android operating systems and came, and there is a need to consolidate the workloads with the mixed criticality and the hypervisor like Xen hypervisor and all. So the more and more it becomes very complex. Now more than hardware, the number of lines of code in software is more and more, and the more it becomes depending on the software for the rich functionality, because customers want to have all the experience, whatever they're doing at home, they want to do have the same experience in the cars. I want to media. Now it's not just a media. They want to have an AI and gamings and all the smartphone seamless experience. So that all push the automotive OEMs uh, to increase the functionality, but also the same time that there is a strong need to reduce the cost of the vehicles and reduce the complexity. So from a 32-bit discrete microcontrollers, it became one single SoC with a lot of software handling all the tasks. That the software become complexity, but that added a lot of complexity from a safety and a security standpoint. If you taken a kind of survey that uh, so the modern car has more than around 110 million, 100 million lines of source code, and it's keep on increasing the complexity. Uh, and the more complexity and more it's a, uh, uh, point of failure for any kind of critical functionalities. So it becomes the more we depend on software, the more so failures and more concerns from a safety and security point of view. If we take a look at the latest automotive recalls, so that all has the software is the main cause for the uh, or the systematic faults are the main cause for the failures of the system, and that has automotive recalls, that triggers automotive recall, because hardware has a predictable failure. They have a bathtub curve. They call bathtub curve. It has some predictability in terms of overall component failure. But software is more complex, and the failure is very, very difficult to predict and mitigate the failures of the software. So that's why we talk a lot about functional safety, and we want to do functional safety. It's not because it is just a buzzword. We want to be in the market. So it's not just the reason, and the reason is that we need to have functional safety because there's a technical requirement, and now the regulatory requirements are becoming more and more strong. So it's a mandatory that we need to comply to the functional safety standards. They talked about this uh, multiple ECUs, discrete ECUs were consolidated to provide more rich functionality uh, and one powerful advanced SoC. Yeah, sorry, thank you. Yeah, yeah. Uh, so I talked about multiple ECUs, and they were consolidated to provide a rich functionality. So the more we consolidate and we relied on software for the consolidation, and because we cannot have all the functionalities to have the same level of safety. So we have a mixed criticality. We take an example of a software defined IVI. We have an infotainment and we have a telltale and we have other safety critical functions. We all got mixed up in a single SOC running in a hypervisor uh, and different operating systems. So that creates a okay, yeah, I think this is better. Yeah. Sorry, my voice pitch is very low usually. Yeah. So this is the traditional. It works very well. Okay, yeah, thank you. So this is a typical use case scenario. So you have an SOC, multi-core SOC, and you have a hypervisor, and then you consolidate an Android system, Android Automotive OS, which has a non-safety critical applications, and also the same architecture has a safety critical applications, which displays all the critical telltales, as well as rear view camera displays, which is safety critical. So when you consolidate these things, so we need to make sure that the non-safety critical or the unsafe or QM, when I say quality managed one, which is running on the same architecture, is not interfering with the safety critical applications. That's the whole idea, because that interference, we need to avoid that interference. Otherwise, your non-safety critical applications will interfere or will crush the safety critical application at a particular timing. Imagine a car running on a highway that you play a media player, the media player is going and killing in a telltale application. So the driver loses all the safety critical information on the dashboard. And then there's a less controllability for the driver when he's driving on the highway, then the safety goal is violated. And depending on the controllability of the driver, you have the potential impact for the injury. The injury can be light or the injury can be life-threatening. So depending on the case, right? I mean, there is a whole lot of hazard analysis and risk assessment when you define a particular safety goal for a particular item. Okay. So yeah, just I put something ASIL and all the things, some safety terminology, basic terminology. So the ISO 26262, it's a functional safety standard for road vehicles. The initial version was released in 2011, and then second version was released in 2018. The next version is going to be released in 2027. So it addresses the automotive safety in two parts. One is that random failures, which is dealing with the hardware failures, and there's a lot of fault metrics. And then it's a systematic failures, which is more towards the design process of the hardware and as well as the software development or the software development process. It deals with all the software failures. So in ISO 2626 terminology, a system is defined as an item. And if you take an uh, IVI domain controller, that's an item. If you take a camera system, that's an item. A powertrain, that will be considered as an item. So the item has different hardware and software components. When you assign a safety integrity level, so that's called automotive safety integrity level. So the automotive safety integrity level is a risk classification scheme as per ISO 26262. And ASIL is assigned to an item depending on uh, the impact it has on the safety of a driver, passengers, and the vehicle. So you have from ASIL A to ASIL D. and ACLA means the lowest level of hazard, like the injury, then that that creates a need to the development and the testing activities. So it goes up to ASLD. ASLD is the highest level, means that the braking system is an item that will have an ASLD criteria. If it fails, then the driver will lose the control and meet an accident, and it's going to be a very life-threatening issue. So that will be an ASLD. So an item which is assigned an ASLD will have hardware components and software components, and the ASLD requirement will be delegated to hardware and software component appropriately in order to ensure that the overall item is ASLD. So we have a software IVA domain controller that's typically it will have ASLB category based on the industry standard, and there's a process called hazard analysis and risk assessment called HARA, and based on that the ASIL is defined and assigned to an item, then subsequent ASIL requirements are relegated to the hardware and software components, which is providing the functionality to the item. So in our software defined highway example, it's an ASIL B, for example, the use case. So the item must meet an ASIL B criteria for according to ISO 26262. Then the ASIL B requirement will be delegated to both the hardware and software components. There may be multiple hardware components, and how they achieve overall ASIL B for the hardware component depends on various factors, and also multiple software components. How if you have a mixed criticality software components, how you are going to ensure the freedom from interference is going to be in a case-by-case design. So in our example that we have Android automotive operating systems, which runs all non-safety critical applications and an ACB safety critical operating systems, which provides a functionality to render camera, display, and telltales, etc. And both work as a virtual machines on top of a hypervisor. So we enter now the terminology mixed criticality workloads and the safety critical applications and quality. So when we in the ISO 26262 context, when we say that a non-safe, unsafe, we usually use the word called quality manager, assuming that the non-safe critical component followed some kind of quality managed life cycle for the development purpose. So now we have ASIL B, a safety critical operating system, and non-safety critical Android. So we cannot have all software components in one single ASIL components. That's why we have to separate is safety critical as a one virtual machine, QM component or non-safety as another one. Imagine that completely safety certifying an Android automotive OS is going to be very challenging considering the code size. So you don't need to do that. So you can have in a container kind of solution like a hypervisor. You can host safety critical or applications in a safety critical OS and all other navigations and media player that can run on a safe Linux. Sorry, not safe Linux. It's an Android or other version also Linux. So when we have this kind of solution at any given point of time, so we need to prove there is no cascading failure in the sense that we need to prove that there is no interference from the QM software partition to the safe partition. So that is the whole idea that we need to provide the isolation. The isolation comes in two forms. It's a spatial domain isolation, and another one is the temporal domain isolation. So the spatial domain isolation, as per the safety specification definitions, the data used by one element shall not be changed by another element. In particular, it shall not be changed by a non-safety related element. So it's all about talking about the memory protections, that a safety critical VM memory owned by safety critical VM should not be interfered by a QM or non-safety critical based VM. And the temporal domain talks about that uh, CPU and other resource usage and the CPU execution time. So we don't want a gaming application to completely hog all the CPU power when there is a need for safety critical applications to use the CPU. So this is called temporal domain or temporal isolation. So by having a safety certified hypervisor, we ensure that the safety critical virtual machine has the memory, which is not affected or impacted by the uh, uh, non-safe VM, uh, and it has the CPU dedicated to run the safety critical workload when there is a need. So it's not impacted. So that has to be ensured. Otherwise, there is no point in having a hypervisor and consolidating the workload. Also, there is a clear requirement from ISO 26262. If you look at if a software partition is used to implement freedom from interference between software components, then we need to ensure the software partitioning software, which is a hypervisor layer, is meeting at least the ASLB, assuming that there is an ASLB safety critical workload running, or higher than ASLB. For example, if you're running a safe Linux, which is ASLB certified or ASLB claimed, and your hypervisor should be minimum ASLB certified or higher than that. It's not go below that, because then that becomes that uh, the the safety integrity of the container layer becomes less, then it becomes a question of the integrity questions. So we want to have a situation, we want to have a solution that the container layer, which is the hypervisor, should be equivalent or uh, higher than the safety critical workloads ASIL level. So actually in claiming a safety certification or safety integrity level, there are various approaches that you can develop a software component from scratch, following the safety critical functional safety standards, or you can take a pre-existing software that's called a pre-existing software element, or common off-the-shelf software, or predefined software in D178. You can take and assuming that a particular software element has some decent level of software quality metrics in place, and we can see the gaps between the current development standard practices and ISO 26262. Where are the gaps? And wherever we feel the gap, we can do some kind of a reverse engineering and fill the gaps and claim the target safety integrity level at software element level for the particular software. So that's the approach that we are taking for the Xen hypervisor. Xen already has a strong open source community process, which is also used very heavily in the security industry. And when I looked at the development practices of Xen, and I did a comparison analysis and how it makes all the ISO 26262 and IEC 6158 standards, and we created a gap analysis and a plan to fill those gaps in order to meet the most highest safety integrity level for the Xen hypervisor itself, so that it can be used not only for the IVI domain controller, it can be used for even more higher safety critical systems like ADAS applications and other systems. Also, the approach is more towards uh, a kind of a combined approach, which meets both industrial safety use cases as well as an automotive safety use cases. So because I will come to that point later. From software safety point of view, the industrial and automotive safety standards, they share a lot of common characters, and it's basically a qualitative attribute for software. So once you claim certain level of safety at the element level, according to automotive, it can be used in industrial and vice versa. So the solution, the safety, uh, it always comes in two forms. So one is the the design features, which talks about the architectural elements, the feature which are already available in the hypervisor, and systematic process implementation. So the design features, whatever the architectural features to ensure certain level of safety, it's leveraged as they are. Then we employed some kind of systematic process to ensure that those features work as they intended. So I'm going to skip a lot of these details because you already heard so many these about cache interference. To avoid cache interference, there are features, and to run even a safety critical operating systems to run in a cache, and memory allocation, it has its own memory, and you have IO protections. Uh, so I have around 40 slides, so I'm going to skip some of these architectural details and come to the core point about how we so this CPU scheduling and all these characters, architectural elements are directly connecting to the temporal isolation property. So it satisfies all the needs from an architectural point of view to meet the functional safety standards. Uh, and more importantly, we have very good error detection and handling, which we cannot mitigate all the errors, but at least we can detect and log errors or notify the upper software layer so that the upper software layers can take an appropriate actions. And the supporting process, the one that we have an open source based development process. We customized that, or we mapped that process to custom V model development, which is required by ISO 26262 and IEC 61508. And we added moreover some verification activities like a coverage and the runtime test, software interface test, hardware software integration test, and fault injection test, under the overall requirements validation with source bidirectional traceability. So we have the traceability from software safety requirements to until the test case and the test results, which is working in a bidirectional way. This is a mandatory requirement for hypervisor, which is being certified for the highest ASIL level. And we have the supporting process like a requirements management, change control, configuration management, and the document management. This process part will look very lightweight for people because they feel that architectural aspects are more important. But without this process, there is no guarantee to ensure that the architectural elements work in the way that they're designed to work. So you have always, I have another slide which talks about the process part. So always, whether it's safety integrity or security assurance, it's always controls or mechanisms plus process, both go together. So without process, you have some sophisticated safety mechanisms or security features. There is no guarantee that that works. So you need to prove that they work as they're designed to work. Otherwise, that feature is available or not available or same. from a safety point of view. So we have some safety specific work activities like a software tools classification qualification. So all the tools which are used in the Xen development lifecycle, so that will be classified depending on the output of the tool, how it impacts the runtime safety, and then we qualify those tools according to the criteria defined by IEC 61508 and ISO 26262. This is a kind of other than the development process, an additional activity, but very heavy activity. It looks very simple, but you take a compiler and try to analyze the compiler output and how it impacts the safety. So that itself is a huge engineering activity. And we have an independent safety management. So we made sure that the safety management part, which I'm doing, is completely independent from the engineering team, because there is a standards requirement that's you cannot be part of the same engineering team and review all the work products being created. So you need to be a little outside of the engineering team to ensure that there is an independency. And independent safety assessment, we are working with a third-party safety assessment authority based out of Germany. So the independent safety management, safety assessment are the primary criteria to meet the ASIL-D certification. So this is a typical custom V model development flow. So we take from high-level market requirements and product requirements, then the software safety requirements, and architectural and design, then the implementation and verification values. It's a little simplified way of doing the V model. We make sure that each and every phase has a traceability, which is bidirectional traceability. So this is an FMEA. It's a simple FMEA, but we analyze the failures, FMEAs of failure mode and effect analysis. You list out all the possible failure modes and analyze the impact of that failure to the final software and also the system. Then you design all the available design level mitigation measures or the mitigation measures the system integrator needs to perform. So we perform that software FMEA, and there will be a software FMEA report. And based on the software FMEA, then you further will update your verification plan or validation plan. So all the software FMEA results will be compiled in the final safety manual. It's the one that final work product, which will be given to the system integrators and customers so that they can integrate the Xen hypervisor in the systems as per our certification criteria. So the certification route we are taking is very difficult. It's okay. This one. Okay. So we have IEC 61508 Part 3, and it talks about how to safety certify a software element which is not developed as per the safety standard. So there's a class called Root 3S that allows assessment of non-compliant development. So this is a class 7.4.2.12, and this has a subsection to Root 3S. You take this road and follow this B requirement, you got to provide a safety manual. And some equivalent classes there in ISO 26262, which is a qualification of software component. So you take a card software component and you perform whatever way the reverse engineering and create all the evidences and certify to a third-party safety certification authority, and you create a safety manual and all the work products, and then that becomes a safety certified particular software element. In this case, it's going to be the Xen hypervisor. So the status, the assessment happens in two phases. One is the concept approval, the concept of approval. We explained the safety concept, how Xen is intended to be used in the safety critical systems, an architectural overview, and all our verification and validation plans, uh, and the implement process which is in place, and everything we show to the auditor, and we get a concept approval to which increases the confidence that what we are planning and will be doing is meeting all the EC and ISO requirements. Then we execute as per the plan and go for the final assessment. So that final assessments will provide a report and a final certificate. So now in the execution phase that we hope to be completing in a couple of years now, or maybe I didn't write a specific date, but it's soon that we will be updating it. So this is overall about safety, and so if do we have time? Okay, yeah, fine. 5 more minutes. Okay. No, this is not the content. Yeah, this is my last slide. So the same use case can be used for cybersecurity as well, because we don't want an app downloaded from an OEM specific app store will come and take control of telltale applications. So that's a security breach, right? So uh, uh, so the saying is that the item is not secure, it's not safe. If the item is not secure, it's not safe. So you claim all safety certifications, but if there is a security breach, a denial of service that comes and take control of a safety critical application to make that safety critical function unavailable, then all your safety claims becomes null. So if it's not secure, then you cannot claim a system as a safe. So because now everything is interconnected, everything is network connected, you have a cloud service in car, automotive systems, you have even a robotic systems will have a cloud background. So there's a lot of security issues possible. So it becomes now that you need to have a cyber security assurance for both industrial and as well as automotive systems. Yeah, there is a standard called automotive road vehicle cybersecurity engineering. So these are all possible automotive security use case. So we need to protect some of the assets like PII, personally identifiable information of user data, CAN bus. There is a CAN injection attacks, OEM software. If you just Google the recent automotive or car hacking or security breaches, I think you will get a lot of information about these things. And we need to define an attack surface, then attack methodologies, what are the methodologies. So this is a kind of yeah, the risk is growing risk in automotive and industrial systems. So we need to make sure that we have an assurance level. So not just the security controls in place, but also some kind of an process implementation to ensure that there is a security assurance. Time is up. Okay. Yeah, we can have a consensus. So what we are talking about is that we have a cyber security assurance level similar to automotive safety integrity level, and we are targeting the highest cyber security assurance level. And if you see this, so if it's not, if you say that the candidate is contributing to the safe operation of the vehicle, then the candidate is cyber security relevant. That's what the ISO 21434 is saying. So, so there is a need to complaint. There is a again, you have architecture solution comes to the architectural features and then process. So this is something that I liked really when a security is a process, not a product. That you put some controls, but that does not ensure that your system is secure if you don't have a sufficient process in place. I hope that you know this, man. So we will have a similar process how we did for automotive safety, and there will be a separate activities for to meet ISO 21434. The same flow follows, but in a different. We're trying to model the safety critical V model development to security critical. So we have FMEA, failure mode analysis in safety, and we have TARA, so it's called threat analysis and risk assessment, which is something similar to failure mode and defect analysis. Okay, this is the certification tool, something how we did safety certification for industrial and automotive, and we will do the similar way security certification for industrial systems and as well as the automotive system. It's planning. So we will soon update about our security certification plan as well. Yeah, that's all. Any questions? Sorry, I was kind of running through a lot of technical because I had around 40 slides. So the time is I had to rush.